Please, guys. Thank you. Oh. Well, welcome to the latest and greatest episode of the Metaphysical Corner, and I am happy to report my head has been found. I am not the headless. Maybe we should shrink one, or I don't know. Welcome to the latest episode. My head was found and reattached, and I apologize for that, but we will now carry on. Anyway, just to recapitulate a little bit where we're at, I know we've been hopped. My last one was kind of a diversion. Headless. It was headless too. But as far as subject matter goes, and I just felt we kind of needed a little bit of a diversion, and now we'll carry on a little bit, but we'll divert again in the future as stuff crops into this feeble brain of mine. And I just want to recapitulate a little bit of what we were talking about, and that is the fact about consciousness and once again, and a lot of people don't like this, but quantum physics or quantum mechanics, however you want to call it, is the central part of this with consciousness, our existence, whether or not we're a hologram or not, which I believe now we are, and so on. So to this video, we're just going to read a little bit from the book. We're getting towards the end of it, but there's so much more beyond that, which we will get into. But as far as one of the greatest, around the first 10 years of the 1900s, when it was thought that light was either particles of energy or photons, or they were waves, it was not considered. It just seemed impossible they could be both. But yet, every experiment after experiment proved that they weren't. Light was both a particle and a wave. Now that may seem insignificant, but it proves. It's like saying matter is only one thing, and it can't be something else. We'll find out that quantum mechanics, quantum physics says quite the opposite. Things can't be two things at once, as improbable as that sounds. So when they knew that light was, once they figured out that light was both waves and particles at the same time, and it showed both, depending upon which experiment you did, this was a very upsetting observation and revelation, and it set a whole new science it launched a new science, quantum physics, because then they had to rethink everything. So anyway, we're going to get with the this chapter is called Communication Between Molecules, which inside your body is happening literally millions of times per second without your knowledge, without your approval or consent. But then again, if they didn't do it, we would be attending your funeral. So it says, as in the previous section, a living organism is an informed chemical system. As long as it lives, it contains an enormous amount of information that's generated and transferred throughout the whole system, and by this they mean our body. Thanks to this information, an organism is able to feed itself and reproduce. Although we do not control or even understand most of it, this information is totally unambiguous to the system. Your molecules do not need a degree in biology or quantum mechanics to decipher it. On the contrary, the dream of many biologists, I reckon, would be to know as much as their own molecules do. Call it instinct on the part of the biological molecules that make you up. In the current model describing the principal mechanism of the exchange of information between biological molecules, it is believed that written information is written in the structure of these molecules. This is critically important. I'll get this in a second. As soon as a signal is given, the molecules start to react. They start to persistently touch one another, looking for a mate. When a key molecule finds its lock molecule, that is a molecule that will trigger another reaction and produce other molecules. And what they're talking about here is primarily enzymes, which I think everyone has heard of. An enzyme is something that speeds up a chemical reaction between two substances without being affected itself. And by that I mean the actual enzyme. This is done through what's called activation energies. But the two products that are going to chemically react have to fit into the enzyme perfectly, and it's purely a structure thing. The structure of the molecules, the structure of the carbon, hydrogen, oxygen atoms, whichever it is. And if it doesn't happen, the reaction doesn't happen. In a given enzyme, of which there are literally thousands and thousands in you, enzymes that is. This will in turn also trigger reactions to the last molecule of the chain is fabricated until information finally reaches its final destination. Although this model has been greatly improved in recent years, it still appears a bit clumsy and does not describe how molecular structure could store information. In the first part of this book, we use diamond and graphite as examples as we describe determining the impact of geometry on the principle of a molecule and its reactivity. And by that they mean, I don't know if you remember, carbon and coal, or what do they say? Diamond and graphite. Graphite's what's in a lead pencil. And it's soft. And a diamond is incredibly hard. Yet they're made of the same exact thing. Carbon atoms. It's the structure between the carbon atoms that makes the difference between graphite and diamonds. Therefore, the study of molecular structures is very important for all researchers, biologists or not, and is the subject of a vast area of research. No doubt many of you would be surprised to learn that ethanol, that alcohol found in wine and in all other alcoholic beverages, has exactly the same chemical composition as dimethyl ether, which you wouldn't want to drink. In each case, the molecules have one oxygen atom, 2 carbons, and 6 hydrogens. But it's how they're structured, it's how they're put together, where they connect, that makes the difference between an alcohol that you can drink and will make you kind of tipsy, and one that will kill you. The position in each of these compounds is different. As you might guess, the properties of the two are quite distinct. Dimethyl ether is a very volatile liquid that, unlike ethanol, cannot be swallowed or even inhaled without danger. In other words, more than a chemical formula is needed to know a compound. Its structure must also be known. How do we know molecular structures? How do we know, for example, that graphite is long layers of carbon laid on top of one another, whereas diamond is composed of adjacent pyramids, which is how it's done? How do we know what water molecules look like? Or a sugar molecule? Even if I tell you that a sugar molecule like glucose, and that's a sugar that comes from grapes, is made up of 12 carbon atoms, 11 oxygen atoms, and 22 hydrogen atoms. They could be arranged in tens of ways. Only one would be glucose. Same chemical formula, just they could be arranged in different ways so that, but only one of them is glucose. Another arrangement, of course, one of the other possible is galactose, a totally different compound that is much less sweet. Today's scientists know the molecular structure of a compound if its molecules are sufficiently well packed and ordered like eggs in a box. Arrangements of this type exist in crystals, and there is, being the crystal guy I am, I think that's where the power of crystals comes from, in that It's in their arrangement. It allows a much better energy flow, of which, don't forget, energy is the currency of the universe. It's a currency of healing. It's a currency, basically, of metaphysics. Okay? I'm going to skip that. I don't want that to confuse you. Okay. In 1962, the molecularologist Crick and Watson were awarded the Nobel Prize for Physiology and Medicine for their 1953 announcement of the discovery, actually not, it was known that DNA was already around, but they were the first ones to figure out its structure. Through the brilliant analysis of the diffraction pattern produced by X-rays hitting DNA, they succeeded in making a great picture of this huge module. But for a few decades now, thanks to computerized simulation, it has been possible to guess the structure of certain molecules without using X-rays. It is enough to feed the computer with the chemical composition of the molecule, the names and numbers of its atoms, and a few assumptions. The computer calculates all the possible geometric arrangements and deduces the most plausible one like a detective. The precision of these images, that is, the degree to which these pictures resemble the real pictures of molecules, is awesome. Chemists frequently use such computer programs to predict or confirm experimental observation, or to see if a particular combination of atoms could result, or could even exist. For example, could a molecule containing 3 calcium atoms, 5 chromium, and 4 bromine atoms be stable? The results help the chemist to determine whether they should even try to make such a molecule. I assume that in this case the computer would say no, but that's not important. What is important is that the equations used by the computer for these calculations are the fruit of quantum theory. The computer is able to predict a molecular structure through calculations based on equations describing the wave packets of the molecule. If a molecular structure contains info, and this molecular structure can be constructed just using the mathematical functions describing the wave packets, we must conclude that this information has its source in these wave packets. In other words, the information that keeps you alive and makes you a unique human being is stored in the wave packets of your atoms and your molecules. Okay? We need to believe that the information stored in the wave packets of a particle that are stored in the wave packet of a particle can be retrieved and understood only by specialists of molecular biology or quantum chemistry. And I have to say, molecular biologists and quantum chemistry are going to become much more of a single entity in the future. You can't have one without the other anymore. But in fact, as previously mentioned, every single molecule of every living organism understands it. Every single molecule of your billions and billions and billions of molecules in you deciphers this molecular information in its own way. The result is that you are a chemical system that knows how to keep its integrity, feed, protect, and reproduce itself. However, if information has its source in atoms and molecules, information exists in all molecule systems and not only living systems. What then is the difference between living matter and non-living matter? What's the difference between a molecule information stored in a bacteria and that in a pound of salt? To suggest an answer, let's learn a bit about information. When we think about the quantity of information we process each day, whether it's TV, radio, or the internet, newspapers, whatever, it's hard to conceive that information can be weighed like diamonds. And yet, in the middle of the 20th century, a young mathematical genius revolutionized the world of communication by developing a new theory called information theory. He defined a new unit called the bit and paved the way for the digital revolution. If weight is measured in pounds, distance in miles, and volume in pints, information is measured in bits. The theory states that the quantity of bits contained in information, we would say the weight of this information is inversely proportional to the amount of uncertainty it contains. In other words, the more probable the information, the higher it is in bits, and the more improbable, the heavier it is in bits. The lighter in bits first, then the higher in bits, I'm sorry. If, for example, an announcement is made through the media that tomorrow the sun will rise in the east, the information contained in this proclamation is 0. Because it is quite certain that tomorrow, as on any other day, the sun will rise in the east. However, an announcement was made that certain phenomenon observed by satellites in space, and according to NASA calculations, that next Monday an enormous meteorite will fall and crush the White House. That's what it says. I'm not making it up. The amount of information contained in this announcement would be enormous and would certainly overwhelm all media outlets. It is enormous because it is totally unexpected. And it is totally unaccepted because it is very improbable. We could imagine information decreasing or increasing as it becomes more or less precise. Let's take, for example, information about the weather on a summer day. Is it raining today in London? The amount of information contained in this message will decrease if the statement becomes less precise and more probable. It is raining today in England, and it will increase if it's more precise or less probable. It is raining in London this morning, or is it raining in Cairo? The more probable an event, the less information it has. Less new information, I guess you could say. Inversely, the less probable event, the more information it contains. Now let us return to chemical systems and to our question, what's the difference between information stored between living and non-living matter? You might be tempted to reply that since according to information theory, an improbable phenomenon contains much information, the difference is that a living organism contains more information than non-living matter. Because dwelling far from equilibrium, a living organism is an improbable phenomenon. Remember, your body, there's that energy thing. You're constantly fighting the elements. The universe wants to put you in a status quo. In other words, at balance with the rest of the universe, and that won't work. That's death. So, in other words, the fact that you are alive is actually improbable. Kind of a wild concept, isn't it? However, this is not the full answer. Since information is contained in weight packets of atoms, the more atoms that are in a chemical system, the more information that system contains. Make sense? In other words, there is probably more information in a pound of salt than in a tiny bacteria. Therefore, even though a living organism contains much information, there is much more biological information than there is quantity. You are a molecular system in constant activity. Some of your molecules are heading towards life. The rest are headed towards death. Every day, several billions of your molecules are ejected from your organism and make way to equilibrium through the gases, liquids, and solids that come out of you every day in your daily life. On the other hand, new molecules are constantly being created. And thanks to energy and matter you absorb from outside of you. We have associated these two processes with the instinct for death and the instinct for life. Indisputably, the replication of your cells is no more essential to your existence than expulsion of dead cells. We can say here, not without irony, that death is vital. It is this constant renewing of old molecules by new one that keeps your system in constant activity and keeps you far from equilibrium and alive. Chemically speaking, you're not the same as you were 5 minutes ago. Therefore, you are not obliged to panic and take medicines every time you feel bad. It will pass. Unlike table salt, you are a reacting chemical system, the molecules of which are temporary. This is another privilege of living matter. Most of its molecules are in transit. They are constantly being renewed. This constant activity keeps your whole system in a metastable state. At any given moment, some of your molecules are moving towards equilibrium while others are remaining far from equilibrium. But there are enough remaining far from equilibrium to keep you alive. If all of your actions were tended towards equilibrium, you would rot in a few days. Now, as we all know too well, this situation is not permanent. Sooner or later, a living organism is transformed into an inert chemical system. There comes a moment when your molecules, still full of information, change direction and begin to move towards equilibrium or death. On the way, they lose the information they contain, which is necessary to maintain the integrity and molecular activity of the chemical system that is you. Sometime after your death, practically nothing remains of the information that made you a whole and unique chemical system. Long fragments of your DNA, if they had the opportunity to be given so, will remain for a time in other chemical systems, those of your dependents. Or not dependents, descendants, I'm sorry. The remainder of your molecules made up of those imperishable items will be launched into the huge molecular system that is our universe, and their final destinies await them through random encounters. I wrote earlier that your molecules will lose the information that they contain, but this is not exact. Only biological information is lost, not chemical information. Molecules cannot lose information, since the latter is engraved in wave packets. That is, it's their nature. So again, what is the difference between biological and information? What is the difference between biological information and chemical information? What is lost when a living organism dies? And that is the subject of our next video. What is lost when a living organism dies? Talk to you then.